All right. So this week's discussion is going to be about properties of light that can't be explained with any of the physics we've talked about so far this quarter. So coming up to this part of the course, we've been thinking about light in terms of a wave. So we've been thinking about how it travels. We've been thinking about how it participates in superposition, interference, and diffraction phenomenon, how it behaves like a wave. But when we look at some experiments that have been done in the past 100 years or so, there are properties of light that can't be explained through this wave sort of behavior, which poses some interesting questions that end up being answered with quantum mechanics and a deeper understanding of how light and indeed particles end up behaving. So the experiment that kind of kicks this off in terms of our discussion is the photoelectric experiment. So in the pre-topic video, I discussed the photoelectric experiment in detail. I'm going to start off just by summarizing that again, talking about some concepts behind a photoelectric experiment, what that tells us about light, and move into what other questions that brings up for us thinking about light. So as a reminder, the photoelectric effect is this idea that if I shine light on a metal, I can liberate electrons from that material. If I catch those electrons, I can count up the current to count up how many electrons I'm freeing from the metal, and I can adjust a voltage in order to see how much kinetic energy those electrons have when they leave the metal. And those would be my dependent variables. My independent variables would be changing the intensity and the frequency of the light. So classically, we wouldn't really expect changing the frequency of the light to do anything. While we would expect increasing the intensity to be like increasing the power and increasing either the number or energy of the electrons being freed from the material. What we actually see is a little bit different, which is if I increase the intensity of the light, actually the energy of each individual electron remains constant while the number of electrons increases. So it's not clear from our way of understanding why that should be so. We might expect both to go up. We definitely have no reason to look at why the kinetic energy would stay the same as I'm increasing the energy that's incident on the material. The other kind of unexplained phenomenon that arises here is that I have a dependence of the result on frequency, right? Classically, we don't think of frequency as affecting the energy. Especially strangely, we notice that below a certain frequency, we don't observe this phenomenon at all. So we start seeing electrons leaving the metal when we've increased the frequency above a certain value. So we call that the threshold frequency. And when we do, we see that the kinetic energy of the electrons leaving the material starts to increase. So that's not something that we can explain with our understanding of light so far, and this leads us to develop a new model for how we think about light. So this is where we come to our discussion of photons. So the idea behind photons is we're going to model light as a series of particles, and we imagine the process by which light kicks an electron out of the material to be something like a collision. Each photon comes in, collides with a single electron, and so if I change the number of photons, I change the number of electrons. We identify the energy in each of these particles as a constant times the frequency. And so this gives us an explanation for the threshold frequency. The idea is below a certain frequency, individual photons aren't energetic enough so that when they participate in a collision, they don't actually kick an electron out of the material. If I look at how this affects my idea of intensity, right, I can think about the intensity as the power per unit area. And so I can interpret intensity in this model as the energy per photon times the number of photons per second. So then that would be Planck's constant times the frequency times the number of photons per second. So increasing the intensity of the light is not changing or if I'm keeping the frequency the same, it's only changing the number of photons per second, which is why I get the relationship where increasing the intensity increases the current detected in the experiment, but not the voltage. So in order to come up with an expression for the kinetic energy of these electrons, I can imagine that each of these electrons has a certain amount of binding energy, or a certain amount of energy I need to add in order to free it from the material in the first place. We call this the work function. So this would be a certain amount of energy corresponding to how much energy I need to give it to peel the electron out of the material. And so any excess energy I give above that amount would correspond to the kinetic energy. So the equation I can write here is that the kinetic energy is the energy of a photon minus the work function, or Planck's constant times the frequency minus the work function. If I want to find the threshold frequency, right, Planck's constant times the threshold frequency, that corresponds to the minimum energy that frees an electron. So that would be equivalent to the work function. So some of the concept questions I asked about this, in this first one, I'm imagining, right, you're sitting at a bench, you put together your own photoelectric experiment, and you don't actually see any current, right? The experiment doesn't seem to be working at all. You don't observe any photoelectric phenomenon. So in this case, that means I am probably using light that is not at a high enough frequency to free electrons. So I imagine that my Planck's constant times the frequency in this case is smaller than the work function, which is going to give me no current. So what I need to do is I need to increase the frequency above that threshold frequency, which is the same thing as decreasing the wavelength. This is another one I really like. So if I am using two lasers, right? Let's say I buy a 5-watt laser and it's green, and my friend buys a 5-watt laser and it's red, and we want to have a bragging contest about whose laser is making the most photons. Even though these two lasers are producing the same power, they actually are going to be producing different photons. And that's because the energy in each individual photon is going to be different. So for red light, the frequency is lower, meaning the energy in each individual photon is lower. So power, right, don't forget, is energy over time. So if I have the same power, the only way I can do that is with more photons per second, since each photon represents less energy. So that means the red laser is emitting more photons per second. So this is really getting into this new understanding of how the frequency and energy are connected, which was just totally absent in our classical model about light. Okay, so in our first quantitative practice problem, we are testing some sort of mystery metal, and we observe that we see the photoelectric effect when the wavelength drops below 600 nanometers. So that should be enough information to find the work function of the metal, right? We can identify what the lowest energy photon will be that will kick off an electron out of this material. And if I decrease the wavelength, right, then my photons are becoming more energetic, meaning that they'll have some extra energy left over at the end of the collision, which will be in the form of the kinetic energy of the freed electrons. So my threshold wavelength is 600 nanometers. I can turn that into a frequency, right? The frequency being the speed of light over the wavelength. And that threshold wavelength, right, I can use find threshold frequency and therefore the work function. So the work function is going to be Planck's constant times the speed of light over this threshold wavelength, if you like, which corresponds to 3.3 times 10 to the negative 19 joules. Incidentally, right, electron volts are kind of a nice unit to use when we're talking about this sort of stuff. So an electron volt is a unit of energy, corresponds to like 1.6 times 10 to the negative 19 joules. And that looks, that 1.6 times 10 to the negative 19, you might remember, oh, that's kind of like the charge of an electron. That's because this is the amount of energy that corresponds to one electron changing voltage by 1 volt, right? So it's literally the charge of an electron times a volt makes an electron volt. And since we're going to be talking about energies on the order of magnitude of 10 to the negative 19 joules, right, it might be nicer to solve this sort of problem in terms of electron volts. So in this case, this is going to be like just over 2 electron volts. So if I now replace my light source with one that has a shorter wavelength, right, those photons are now more energetic, meaning I'll have some extra energy left over when I'm done. Specifically, I can take the hc over lambda corresponding to the energy of a photon and subtract the work function in order to figure out the conservation of energy, and that will give me 1.1 times 10 to the negative 19 joules, which corresponds to something like 0.7 electron volts. For part 3, I asked kind of a weird question, which was, what would the voltage be on this experiment? Like if I was playing with a voltage knob to try to measure this energy, right? We have to remember like how voltage works and thinking about how the change in potential energy looks like the voltage times the charge. So the difference in kinetic energy plus the difference in potential energy would be 0 if I've got the voltage cranked up, right, as high as it can go while still seeing a current. So I am going to find a potential energy that perfectly cancels out this kinetic energy and then divide it by the charge of an electron to figure out what that voltage would be. And I arrive at 0.7 volts. And so it's not a coincidence that our energy was 0.7 electron volts. And then as a result, that means one electron can overcome a potential difference of 0.7 volts. It's just one way in which this electron volt unit is just really convenient to use. Okay, so one more practice with this same kind of equation. We look at lead with a known work function in terms of electron volts. We can identify, right, what wavelength is going to correspond to the longest wavelength that gives me a signal in the experiment, and then replace that with a 250 nanometer laser to find the voltage in the current. So, right, remember 1 electron volt is 1.6 times 10 to the negative 19 joules. We can choose to work in either unit. If you want Planck's constant in terms of electron volts, this is what it looks like, 4.14 times 10 to the negative 15 electron volts seconds. So that times the speed of light over the work function will give me the threshold wavelength, which I arrive at 291 nanometers. If I replace that with 250 nanometers, then that means there's going to be some extra energy left over. hc over lambda gives me the photon energy minus the work function. I have 0.77 electron volts. So that means the electrons that are freed in this experiment can overcome a voltage of 0.77 volts. If you want to think about current, right, then we just have to remember that current is equivalent to the amount of charges passing by every second. So I can break down current into the charge of an electron times the number of electrons per second. I can also make some assumptions that, hey, maybe we can say that the number of electrons per second are corresponding to the number of photons per second. Okay, well, how do we find a number of photons per second? So that we can figure out from the power. If it's a 10-watt laser, then that power corresponds to the energy per photon times photons per second. So from there, we can figure out the number of photons per second. It's about 10 to the 19 photons per second. And then I can put that, if I say that's equivalent to the number of electrons per second, then that would correspond to an operating current of like 2 amps in the experiment. There's a little bit of an assumption in there, right? Who's to say for sure that every single photon is successfully freeing an electron? You could probably argue that there should be some coefficient in there representing like the experiment not being perfectly efficient, but I think it's a fun kind of question anyway. Okay, so that's the photoelectric effect experiment, and it gives us this model of photons. For me, as soon as you have this new model of photons, I think it provokes a lot of other questions, right? So some of the ones that come up a lot for me are, well, okay, if I think about light and I'm claiming it's a particle, then can I say it has momentum, right? If I say it's a particle, well, then how big is it? And if I'm saying, hey, light kind of behaves like a wave, kind of behaves like a particle, then I might want to ask, like, what's so special about light that it gets to do this? Like, what about other particles? Can they behave like waves, or can they behave like like both waves and particles too, or is it something specific to light that gives it this property? So let's go to the first question, right? Thinking about, does a photon have momentum? And yeah, actually, we can model the momentum of a photon in terms of collisions. And so a collision where I have a free electron floating in space and I shoot a photon at it, that's called a Compton scattering experiment. So we can do this experiment and we arrive at this idea that the momentum of a photon is going to be given by Planck's constant over the wavelength. So when the photon hits the electron, right, I have a collision, and then the photon heads off, having given up some of its momentum to the electron. Well, you know, typically when we think about this sort of collision, we would say, okay, well, if something gives up some momentum, it slows down. But we know that the light is always going to be traveling at the speed of light. So we have this strange case where the momentum of the photon has nothing to do with its speed, which is kind of odd. But instead just has to do with its wavelength. So we can actually, well, we need a little bit of special relativity here, but otherwise this just kind of looks like the same old 2D collision that we might have done in 121, right, where we're just keeping track of the initial and final momentum in vectors and the initial and final energy. So if we do that, we can arrive at this idea that the wavelength is going to change by an amount that depends on the scattering angle. So the idea is that the bigger the deflection of the photon is, the bigger this angle is, the more momentum that the photon has given up to the electron. If it's barely deflected at all, then its momentum should have barely changed. And so this leaves us with our Compton scattering equation, which is that the shift in wavelength, so the new wavelength minus the old wavelength, is going to be a constant times 1 minus cosine theta. We can do this in terms of quantitative problems, right? If we have a wavelength photon scattering off an electron, and let's say we're looking at a case where it scatters off at an angle of 90 degrees, what is the new wavelength of the photon? One thing we find is that the Compton scattering shift in the wavelength is quite small. So our normal wavelength we think about as like 540 times 10 to the negative 9 meters. The amount by which the wavelength changes is going to be something on the order of like 10 to the negative 12 meters. So it's a very tiny fraction of the wavelength that's going to change here, even with quite a large scattering angle. But it is measurable, and you can actually do this experiment if you have the right setup. One thing we do notice here is that the final wavelength is longer by this amount. So, right, let's go back to the momentum. Right, the momentum was Planck's constant over the wavelength. So a bigger wavelength is a smaller momentum, right? The momentum of the photon has decreased in this collision. Okay, so the second of the three kind of questions that, you know, the whole model about photons brings up for me is how big is a photon? And this is a point where I can completely, without sarcasm, respond with the question of why is the sky blue? Because it turns out that these two questions actually have exactly the same answer, which is kind of great. So when we talk about how big a particle is, we typically think about that in terms of collisions, right? There's no real way to take something the size of an electron and slap a ruler next to it and measure, right, the height of the electron. Instead, how we think about it is we shoot these two particles together at one another, and we look at how likely they are to hit one another. So this is a little bit like measuring the size of a bowling ball by how likely it is to hit a pin after if you keep throwing it at random angles down a bowling alley. So we can kind of figure out the cross-section in terms of area by relating it to the probability that a collision takes place. So we can come up with an experiment where we find the cross-section of a photon by shooting it at different particles and finding this probability. And what we find is kind of interesting, which is that the size of the photon actually depends on the frequency. The photon is more likely to engage in a collision if it has a larger frequency. The relationship actually goes like frequency cubed. So this experiment is called Rayleigh scattering. And you can get the exact expression either from data or from a really careful model of the cross-section. And the model you have goes like frequency cubed. So that means blue photons are much more likely to collide with a particle that they fly past compared to a red photon. And effectively, a blue photon is bigger. It takes up more space and is more likely to collide. So if I imagine light coming from the sun as being made up of photons of different colors, the lower wavelengths, so like the blue light in particular, is larger photons and therefore more likely to collide with stuff as it makes its way through the atmosphere. So if I'm standing here and I look up at a portion of the sky where the sun is not in the sky, photons arriving at my eyes from the sky have not come straight from the sun. They've come along a bit of a bouncing path, right? So they've bounced around the atmosphere a little bit before they get to me. And the photons that are more likely to have done that have higher frequencies. So hence the color of the sky being the spectrum of the sun, but where I've weighted it just really heavily towards higher frequencies. Meanwhile, right, if I look straight at the sun, don't look straight at the sun. If I look straight at the sun, then I'm going to see predominantly red and yellow photons that make it straight through the atmosphere without colliding. And variations on this are why, like sunsets, for example, can be quite colorful. Okay, so then that brings us to the third of my three questions, which is what's so special about light, right? Why does it get to have wave things and particle things about it? And so if I want to ask, like, well, can something like an electron have wave properties? There's different ways I can try and do that. I think diffraction is the kind of most wavy thing, like wave-like thing that I can think of. Like diffraction is just something that we would not think of particles doing, right? The idea of bending around corners and about like spreading out a beam into like a central peak, depending on the width of the slit, right, isn't something we think about with particles. If I think about particles, right, if it fits through the slit, it should just go straight through the slit, right? It shouldn't bend around any corners. So if we can make electrons do diffraction, then they have some sort of wave property about them. And we can actually, if I shoot electrons through a sufficiently narrow slit and I let the experiment run, right, I can observe a distinct pattern in where the electrons hit the screen. So electrons will predominantly hit the screen towards the center, but they will be some that hit off center, and there will be some points where I never see an electron hit the screen at all, regardless of how long I run the experiment. So we arrive at a situation where I can actually trace out the probability of an electron hitting the screen in a particular spot, and it looks exactly like the intensity of a diffraction pattern. So this gives us an idea of what the effective wavelength of an electron is for wave-like experiments, right? Electrons will participate in diffraction if the slit is comparable in size to their de Broglie wavelength, which is defined as Planck's constant divided by their momentum. So this is making use of the same definition we had for the momentum of an electron, right? Where is Planck's constant over the wavelength? So we flip that around and say, okay, well then everything has this kind of wavelength if we take Planck's constant and divide by its momentum. And it's true. It's not always practical or interesting or useful, right? The key idea here is that the length has to be on the order of the de Broglie wavelength for us to see these wave-like properties. And so this, in a roundabout way, explains why most things we see don't experience wave-like properties in our daily life. So for, say, like an electron, a proton, and even a physics student, we can identify their de Broglie wavelength, and that would give us a length scale on which the wave-like behavior of these objects would become important. So in each case, I can take Planck's constant divided by the momentum. So just mass times velocity, right, for classical particles and momentum. And what we find is if all of these objects are moving at, say, 100 meters per second, the electron has an effective wavelength of around 7,000 nanometers. So if I'm doing an experiment with length scales that are relevant, right, in thousands of nanometers, I will see wave-like behavior of an electron. And so that's actually relatively easy to do, right? We were seeing diffraction experiments of light around that sort of length scale. So we know we can see those. Protons, well, those are more massive, so they have a shorter wavelength, down at 4 nanometers. So that's tiny, but still doable, right? So you can imagine I can come up with, it's going to be trickier, but I can come up with a proton diffraction experiment and observe that. If I wanted to observe the wave-like properties of physics students, I would need to use a slit that was a size of 10 to the negative 38 meters. So I would need to shoot students through a slit that's 10 to the negative 38 meters. It's not super practical. The length scale between the nucleus and electron is around about 10 to the negative 10 meters. So we're talking about a length scale that's impossibly tiny, even if I'm living in the space between a nucleus and its electron, right? So yes, you are all waves, you all have wave-like properties, but the length scale on which these become relevant is so impossibly small that it's just not something we encounter or deal with in our daily lives. So in terms of how we do diffraction problems with electrons, it's really the same sort of equation that we've been using, right? This with W sine theta is equal to lambda for the first diffraction minimum. And so we can identify the wavelength of the electron using the same old diffraction equation. And then I just need to use the de Broglie wavelength in order to figure out, right, how fast it's going. And so I can find the velocity as the momentum divided by the mass, or Planck's constant divided by the wavelength and mass. And so that gives me somewhere around just under 5,000 meters per second.